class, so in the afternoon session, will be given by Simon. And actually, we have a slight change for the titles. It's different from the conference group. So the title, the new title, will be Spikes and Stimuli.
It's quite abstract in your book, the title not spotting around. Yes, I'd like to actually sort of, well, first of all, let me thank everybody for the invitation. It's wonderful being treated like and I'd like to sort of move on from what Michelle was talking about very fast categorization, talk about some of the mechanisms that might be going on in the brain, which has been an interest of mine for a very long time. So Michelle chose this thing with the animals, and that clearly, you get the idea of categorizing images. But it's not just categories we can do. So we can add in, do the same thing, but throw in an odd man out image and ask you, can you see the odd man out? So now it's not a category, doing a category task, but trying to identify a particular image. So watch this, and did people see the Mona Lisa? Right. Okay, how about this one?
Oh.
You see this statue of Liberty? And how about this one? You say it's the Mickey Mouse. So Mickey Mouse is an animal, but it jumps out at you. So my feeling is that even if you're not trying to do a task, images, you can sort of, your visual systems process them. And so, it's actually activating memories effectively. So if I just sort of, I don't know whether these all work for people in Taiwan. These are things which work well, certainly for me. You probably get you've got a whole set of things that wouldn't mean very much to me, but we all share these things. This is 2 frames a second, and you really get the impression, if you know the stimulus, that you've got it. I mean, your visual system has done the whole thing. That last one, does everybody know what that is? I mean, this is that's that Dalmatian picture from Psych 101, which many lecturers will give you. This is really interesting, I think, because even 10 seconds during a lecture. I've found plenty of people who haven't done psychology like 15 years, and you flash that up, and they'll say, "Oh, it's that Psych 101 picture." They've stored in a few seconds. If you can get the students interested, they will store this, and it's in their brains, and somehow the brain has stored a sort of engram of that image. So the sort of questions I'm interested in, well, how do we do this recognition so efficiently? And also, can we imagine building a machine that can do this? I used to think it was totally impossible, but you'll see that actually we're getting there. And the other interesting thing is, how do we learn to recognize new stimuli? How do we do this 10 seconds of looking at a Dalmatian picture? Oh, everybody knows this is Dalmatian. What's happening when you do that? So I'd like to go back even pre-1996. I've been worrying about how the temporal constraints on processing constrain models. This is an old paper that I did, which is actually based on the fact that I was in Edmund Rolls's lab when I was doing my thesis, and this is Dave Perrick's paper from 1982. These are neurons in the top end of the visual system that are responding selectively to faces. And they do this at 100 milliseconds after the stimulus came on. And so I was just thinking about this. This was the time when parallel distributed processing models were coming in, and I said, well, we know that these neurons here are at the top end of a whole series of processing stages, going from the retina through LGN, B1, B2, B4, IT. That's about the shortest way route you can get there. And it struck me that. I made so this is back in 1989, that given that you've got about 10 processing layers, you have to be able to do this pretty much in a single feed-forward pass. Why? Because any of these loops would probably take like at least 10 milliseconds to kick in. So when you're getting these fast processing, you probably don't get to get the loops to work. And there are lots of anatomical loops in the system. Also said that probably, since you have to go through 100 milliseconds in 10 layers in 100 milliseconds, that's 10 milliseconds per processing stage. A typical neuron, even if it's firing fast, will generate one spike in that time. So you can't even measure firing rates accurately. It has to be done with a really, really crude processing. So you can't use firing rates, can't really use loops and so on. But this was all based on, hand waving, back of an envelope calculations. We didn't really have any tight evidence that, real vision as opposed to phase selective neurons in monkeys could be done like this. But of course, as Michelle was saying, with this sort of experiment, where you have unpredictable stimuli and you're doing, is there an animal present? And we got, these sort of reaction time distribution and so on. 150 milliseconds was clearly enough to do the whole lot in humans. And as Michelle said, humans are actually slow compared with monkeys. So the monkey data really, really puts very severe constraints. And you've already seen this, but basically you can go through, sweep through all this lot in 100 milliseconds in a monkey and get to the top end of the visual system. It really does look like a feed-forward processing sweep with only a few milliseconds per processing step, because actually a lot of this time is not processing, it's just getting spikes from A to B. The neurons that send information from V1 to V2 to V4 and so on, they've got conduction velocities of about 1 or 2 meters per second. So going from here to here is going to take 100 milliseconds just in conduction delays. So this is, really sort of tightens things down a lot. You probably only got one spike per neuron, very sparse coding, very few neurons will actually get to fire during that wave of spikes, I would argue. And probably without much help from context, because if you can, even if you don't know what you're looking for, and I flash up the Mona Lisa, and you can activate the neuron at the top end of the visual system. And Michelle mentioned Christian Kaiser's experiment where they have RSVP and look at little blips in the activity of neurons in IT. They can cope with up to 70 frames a second and still get processing done. Now here's an interesting question. What's the state of the art in computer vision? I mean, until a few years ago, I said, human vision, there's no way we're going to ever get there. But the fact is that computer hardware is getting more and more powerful. So, if we take the brain, here we've got a simulation of 16 million neurons here. In the brain, there are actually 86 billion neurons, 16 billion of them are in the cortex. Let's say about 4 billion of them are in the visual system. And they've got this clock that a neuron literally physically can't fire more than 1,000 spikes per second, and it almost never does more than 100 or so. And there's this killer problem here, the slow conduction velocities, unless you're in the pyramidal tract, where they're really big myelinated fibers. Most of the fibers that you're doing vision with are really quite slow. But of course, the brain's great because it doesn't use very much power. Let's compare that with state-of-the-art computers. Well, if you go out and buy a graphics board, you get 4.5 teraflops. That's a million floating point operations a second. Thousands of cores, billions of transistors, lots of memory bandwidth, 200 watts. It gets rather hot. But they're cheap. So the question is, what can we do with this relative to the human brain? Well, as I say, I thought, no way. But the ImageNet challenge is the sort of the really hard task for computer vision people. They give you 10 million training images with thousands of labels, and you train up your system, and you come in, and then they give you hundreds of thousands of new images, and you have to label them, and they score you on how good your labels are. So this is a bit like our experiment. You flash up an image and you have to say something sensitive. Well, I was at the European Conference on Computer Vision in Firenze in 2012, where everybody was talking about this competition because it had been won by a feed-forward convolutional neural network. Basically, nothing very surprising to neurophysiologists. It's trained with the back propagation learning rule, which is not very biological, to put it mildly, but basically the system in the end is really dumb. So it's called supervision. Jeff Hinton and his two students did this work. And here's the architecture. You take an image and you run through a bunch of layers. In fact, so you have a bunch of convolutional layers, a couple of fully connected layers, and these are the output layer with the labels. And they give you all the, here are the numbers, you know, here's the image coming in. It's got, this is sort of V1, it's got, it's 55 by 55 hypercolumns, each of which has got 96 different filters. And then it goes through a bunch of other things, and nobody's done the neurophysiology of what these neurons are doing. But I can show you the first layer. Here they are. These are the 96 filters that were learned by the system. And you know, anybody who's done neurophysiology knows that this is what you get in V1, right? I mean, they're just a bunch of Gabor patches and oriented filters, some color as well. In the whole system, there are 650,000 neurons. There are 60 million parameters to train. And what's the really hard thing is getting the training done. There are 630 million synapses. Okay, but the performance of this system, I was truly gobsmacked. This is Alex Krajewski, the student, just sent me 18 just randomly chosen pictures of animals, and I've ranked them in terms of how well the system performed. So for each image, these images the system has never seen before. This is the correct answer, the sort of the ground truth, and these are the 5 best labels generated by supervision. And this length of this bar tells you how confident it is. So this is a sea slug, and it's like 95% confident in this sea slug, but it might be a flatworm, coral reef, sea cucumber, or coral. These are all very sensible answers. Brown bear, very confident, actually 100% confident, but it could just about be an otter, a lion, an ice bear, or a golden retriever. Jellyfish. All of these are all doing fantastically well. Howler monkey, spider monkey, etc. The errors are just not errors; they're just good guesses. Even this image, you know, which has nothing to do with any. It got that it was a mite. Black widow, cockroach, tick, starfish. These are all pretty sensible. Now it starts getting it wrong here. Okay, so correct answer is spider monkey, and it said it was a howler monkey. Spider monkey came in number 2. Well, look at these two images, and can anybody here tell me which one is the spider monkey? Which one is the howler monkey? It's got this one wrong. It should have said night snake. It said hognose snake. Should have said rough grouse, and it said partridge. Came in second with this one. Chimpanzee came in number 3. It thought it was a gorilla. This is a Gordon setter. It didn't even get it right at all. It thought it might be a chihuahua. Sorry, these are all fairly obscure terms. But this picture is terrible, right? You can't even see the head of this. And this is my favourite. The correct answer is cherry, and the stupid system said it was a Dalmatian. Got it wrong. That's an error. Okay, he actually said great elderberry and currant. When I saw this, I thought, wow, these guys have cornered the market, right? I mean, they know how to do it. Jeff Hinton set up a company with his 2 students, NDNN Research, and they've been bought up by Google. A similar sort of guy, Yan LeCun, also a pioneer of feed-forward convolutional networks from the 80s, is now working for Facebook. So you can expect that within the next few months, you're going to be able to take the phone out and show it things, and it will tell you that it's a chihuahua or a golden setter or whatever. And the amount of memory needed to get this to work was, if you remember, it was 60 million parameters. That's 60 megabytes. I suspect people are going to be able to do this on a mobile phone without even being connected to the web. You need quite a lot of processing power to get it to work. But it's quite uncanny. And then when you compare supervision, this is supervision. This is the primate visual system. It's essentially the same thing. It's even got the similar sorts of numbers of layers. And I wrote to Alex Krzyzewski and I said, you must have just stolen the plan from the primate visual system. No, we just tried various things. This one worked well. In other words, it's convergent evolution. The guys doing computer vision have ended up with a feed-forward convolutional neural network with no loops in it, no horizontal connections, and it's managing to do this really hard stuff really quite well. So you might say, oh well, problem solved, let's all go home. Who will have got the answer? Well, not quite, because it's using backpropagation, which is very slow, and it actually needs billions of training examples. The only reason why this works today, and it didn't work when Jeff Hinton and Jan LeCun were doing this in the 80s, is they didn't have graphics boards at the time, as far as I can see. Because Alex Krzyzewski, who trained up the system, did it all in his bedroom with a computer with 2 graphics boards, because it takes, and this is where I just completely fell over. It takes 1 millisecond to process each image. Well, actually, that's not quite true. Alex loads up 100 of these images, and he gets all the answers down in 100 milliseconds because of pipeline process. So poor old human visual systems taking 100 milliseconds, sorry, we've been beaten. This works, this is 100 times faster. Problem is, it's totally unbiological, and we don't learn to recognize dogs and cats and all the rest of it like this. Nobody shows human children, 100 million photos of dogs and 100 million photos of cats and gives the labels. So here's my plea for biology, please. I don't think this is how we learn, but what I'm going to try and convince you is that what's really important to get into a system are spikes. These systems don't use spikes. They're all floating point numbers and convolutions. And spikes give you 2 things. One is you can use a wave of spikes. So rather than sending floating point numbers, which is what supervision does, we just send a wave of spikes to the system. And we use the fact that the most strongly activated neurons fire first, and so we can actually pick off the front of the wave and get very efficient processing done that way. Because you can use the order of firing of neurons as a code. And the other thing you get is things like spike time dependent plasticity, which is a learning rule which will change the weights in connections between neurons depending on the relative timing of input and output spikes. I'll try and show you how this works. Because what I'll try and show you that these 2 rules together allow neurons to become tuned to things that occur frequently in the environment, and that's so with no labeling you can get the system to learn. But a little bit about coding with spikes. A neuron is essentially a capacitor with a threshold. So if you've got a weak stimulus, it takes longer to get to the threshold. As you increase the strength of the stimulus, it fires earlier and earlier. So if you flash up an image onto the retina, you're going to activate a wave of spikes where the first neurons to the fire actually correspond to the places in the image actually where the contrast is highest. So if you take the optic nerve, it's got 1 million fibers in it, and here are photoreceptors and the ganglion cells. Actually, it's all flipped around the other way around. But these are essentially doing little convolutions. Take 3 photoreceptors, feed them into a ganglion cell, and as you increase the local contrast, the neuron will fire more quickly. And we've showed that you can actually get remarkably efficient processing of an image by having multiple scales and using on and off center cells, as in the retina. You have a sort of push-pull thing where you're detecting bright dots on dark backgrounds and dark dots on bright backgrounds. So here are neurons going up to threshold and generating these waves of spikes going up the optic nerve. And here we've got for a small image, this is the number of spikes that we've used, and you can just sort of say, how long do you need to recognize who this is with Charlie Chaplin? Well, you don't need very many, because if you're reading off spikes in the order of which they're firing, then this is the most efficient way to get the data. So This is one of the keys to why our visual systems are so efficient, is because we send the information by definition in the order of how important they are. So bright spots come out first. You know, if you were lying on your back at night and you open your eyes, the very first ganglion cell in your retina to fire is the brightest star in the sky. You've just done a massively complicated thing with one neuron. It's the first neuron to fire. So here's just to illustrate the idea. You can do this with these are reconstructing images using just a set of on and off center receptive fields, and we're just every time a neuron fires, we plug in its receptive field in the image in this image, and we're doing it in a way where the first neurons to fire work both. This is perhaps I could just show you here. The point at which you realise that this is actually a fox is after when you've only got 0.3% of the cells that fire the spike. This is very efficient. The other idea is learning with spikes. Okay, so spike time dependent plasticity. I'll try and show you this is a way of naturally getting neurons to become selective to things that occur frequently. So this is the basic idea. We have a neuron with synapses coming in. If one synapse fires systematically before the neuron fires, its weight gets increased and other ones drop away. The standard rule is this is the sort of thing that people tend to use in modelling. This is the change in the weight of this relative to the interval between the incoming spike and the outgoing spike. If you fire after the neuron fires, you get depressed. If you fire before, you get really enhanced. Actually, we use a really dumb rule. All synapses get depressed except those that fired just before the neuron fired. So this is a really reduced complexity learning rule. But it has this neat consequence, which is that if you repeatedly activate a neuron with a pattern of spikes, it will concentrate high synaptic weights on the early firing inputs. So here we've got a neuron with 12 inputs. Let's give them initial weights of 0.25, and we'll set the threshold for this neuron at 3. So in other words, all 12 inputs have to fire to get the neuron over the threshold, and we're going to have a repeating wave of spikes, which would correspond to some pattern in the retina or whatever. So on the first presentation, here come the spikes. They all have to activate their synapses to go over the threshold, but when they do, they all get reinforced because they all fired before. Now on presentation 2 of the same pattern, maybe we only need 9 of them to fire to get over the threshold because we've got bigger synapses now, and so 3 of them will start dropping away. On presentation 3, maybe we only need 6 now, so 6 get reinforced and the other 6 start dropping away. Presentation 4, let's suppose we only need 3. And so within 6 presentations in all, we've cleaned up the neurons. So it now has 3 fully potentiated synapses and the other 9 have dropped away. Now the neat thing about this is we've actually just picked off the first 3 neurons to fire on the input. And it did this in 6 trials. And if you've got multiple units with different weight sets that you can have inhibiting each other, you can actually pick up more complicated patterns. So here we've got 4 neurons tuned into 4 different sets of patterns. And so if that pattern goes through, all 4 neurons will fire, even if they're embedded in noise. So you'd have a hard time telling me whether this was interesting or not, but it is actually interesting, that neuron. And you can do this and have a next layer neuron which will pick up those combinations. But that's a toy problem, right? 12 synapses. Does it work when you scale things up? Well, yes it does. This is what we showed some years ago, where we actually had, here we have 100 inputs in the figure. There were actually 2,000 inputs in the simulation. This was a simulation. These are 2,000 inputs with just random Poisson processes with varying things. It's just complete noise, except that we we've taken a bunch of 50 milliseconds of activity here and just copied it and replaced the random intervals. And the remarkable thing is that one neuron, if it's listening to these 2,000 inputs, will, it's just an ordinary leaky integrated fire cell, will very rapidly learn to become selective to that repeating pattern. So initially, here's the neuron firing spikes about 50 times in a second. Here's the pattern which we're going to repeat. And every time it spikes during the pattern, it's going to selectively reinforce synapses which are part of the pattern. Within 5 seconds, the system has tuned in and is now responding selectively to the pattern. And within a few minutes, it's now firing at the beginning. It's backtracked to find the beginning of the pattern. So this is pretty amazing. This is one neuron on its own has found a repeating pattern in this incredibly noisy background activity. Let's forget that. But it turns out whether with more neurons they'll tune into different parts of the pattern, or they'll tune into. For instance, here we've got 3 different patterns, and with 3 neurons, each neuron will tune into a different pattern. It's just a sort of a system that sort of learns on its own. And we've used this sort of thing in a more complicated architecture, to learn to generate face selectivity. So here, what we've got is, these are faces from the Caltech face database, and we've got actually 3 types of neurons. There's red neurons, green neurons, and blue neurons. They initially have random connections. You can see these neurons are firing, these are maps of neurons actually. They're firing it fairly randomly, but you can see that the receptive fields of these neurons are gradually sort of evolving. And this blue cell, for instance, is tending to fire at the bottom half of the face, and you can see why. Its receptive field is tuning up. The red cell is now firing at the top of the face. And this green cell, I'm not quite sure yet, but it's tuning into the eye and the nose. After it's only seen about 100 of these images, and it's already tuned in to features of faces. Nobody told it anything about faces. It's just done this spontaneously because that's what happens the most often. So unsupervised learning. That's with flashed images. We've done the same sort of thing with continuous input. This is Toby Delbrook has developed a spiking retina. It's not like an ordinary webcam. Each pixel fires spikes, which can either be black spikes when the luminance drops, white spikes are the ones when the luminance increases. And you can probably guess what this is, right? A highway, indeed. It's the Pasadena Freeway. That's harder. Now, we took the output of this. It's 128 by 128 pixels with 2 types of cells. That makes actually 32,000 different types of neuron, if you like. And we just fed those into 60 neurons with this learning tool. Really simple learning tool, as I say. This is 10 of the neurons right at the beginning, okay? And you can see these receptive fields are just noise, okay? And now, I'm going to show you the first, every time this flicks, this is in real time effectively, every time it flicks, it's the neuron is fired and it's updating its weights, okay? So after 12 seconds, we're here. After 30 seconds, you can see that it's going darker, you're getting the weights are dropping away, except the particular areas. And here, in fact, after 90 seconds, it's just been watching the spikes coming out of this retina. Within 90 seconds, it's created neurons which are actually good at counting cars on the freeway. And nobody told it what to do. It just spontaneously developed selectivity because these packets of spikes happen to occur frequently in combination. So all the system is doing is just learning about statistics of what patterns of spikes occur frequently. So I was talking at the break about the connectivity between neurons in V1 could be learned by this sort of way. You just have, A edges which are aligned, they occur more frequently, and that will connect up neurons and do that sort of thing, depending on experience. So this system has effectively learned to recognize cars with no instruction. So unlike the supervision system, which needed 100 million labeled things of cars and dogs and all the rest of it, this system generates its own selectivity. And once you've got the selectivity, it's easy to label. So the child sees dogs and cats wandering around, and one day you say that's a dog and that's a cat, and that may be enough because you already have the representation. So this is a very toy system, but I mean we can add more neurons, we can add more layers of processing. We haven't done this yet, by the way, but we can increase the resolution. Rather, we can move up to a full resolution. You just need more neurons, but the basic processing would be the same. We could use more sophisticated input processing and Mexican hat convolutions and things like this. And we don't have to use vision. We can use auditions, somatosensory system. In fact, you can throw everything in together, and the neurons don't care. They don't know these neurons don't know that they're handling visual information. They'll be just as happy with a mixture of visual and auditory stuff. So multi-sensory patterns will be learned as well. So maybe just one last point is that we've got this supervision. I think Google and Facebook, they're going to be providing systems which can do hard vision problems, but they can only recognise things that they've been trained to recognise. You have to label all the data to get it to. This sort of system potentially would be very different because it would be able to learn in an unsupervised way, and it will just generate selectivity whatever happens the most. And if you trained it in a particular environment, then it would generate neurons to cover the set of the things that happen. And actually this allows you to do interesting things like sounding an alarm if something is happening which you can't explain, which is just one last point. These sort of architectures can actually be built into electronics. So there are various people working on memristor-based architectures where each synapse is like a little electronic resistor that you can program. So that, this would be moving away from conventional computing. Rather than using a sort of von Neumann architecture with a CPU and separate memory, this is combining everything together, processing memory and everything. So, hopefully, Michelle sort of was talking about fast visual processing. I think we now know that a feed-forward pass actually can do really hard stuff. Supervision, Google, they can do this sort of thing now. And I think we're in a position to explain how it is possible for an architecture which is just 10 layers of neurons can come up with hard answers to hard problems very quickly. In those systems, they don't have spikes, but I would argue using spikes gives you a lot more. It makes coding much more efficient. You don't have to send floating point numbers. It's just a wave of which spike fire, which neurons fire spike first, and it's more efficient for learning because you can use this STDP learning idea for finding repeating patterns. So and a few tens of presentations are enough to learn this. So configurable perception, for me, is very much as a question of how many times do you have to show faces with the eyes in the top and the mouth at the bottom for the system to start learning about this. And I don't see any real limit to our ability to store new patterns like that. I think potentially we can move towards systems for computing which are very much related to how our own brains compute, which I think is an interesting possibility. So. Credits. So the STDP modelling stuff, which I mentioned, Ruth and Rudy and Tim were very much involved in that. And this other stuff, the learning of cars, this was done with some people at the CEA, atomic energy research thing in France. Olivier Bichely was a student who did that one. And obviously we're building up very much on all the insights that we've got from the sort of experimental work that Michelle was talking about earlier on. So thank you very much.
the way traditionally the recognition problem being sort of conceptualized, if following, say, David Marr's idea, then the importance is extracting the invariance about the changes across the images, and then also, say, test to see whether the system can generalize to some views or some other changes that it hadn't encountered. So would the system achieve that kind of functionality?
Yeah, so for instance, I mean, we saw in the case of the learning faces, you had 3 types of neurons, and the neurons in the end were like sort of an average face. Simply because that you will pick up on the thing which is constant. So, and you can explain things like race effects. The Caucasians are better at recognizing European faces, and Asians more Asian faces, because they get more experience with it. So I think that fits with the idea that neurons essentially are trying to find what doesn't change very much. That's what they do when they choose a particular set of weights. It's the stuff which is the most reliable. So I think you could probably fit that with the sort of David Marr thing of what doesn't change very much when you rotate an object and so on. It's because those are the things that get repeated most. So what you don't want is a thing which only ever occurs with a particular view. You want a thing which is robust as you move the object and rotate it in 3D, for instance. And those are the things that you learn better than just random patches of image, which will probably not occur very often.
Any other questions?
Yes.
Thank you. That was a really nice talk. I think it goes a long way to solving some of the questions that were asked earlier about what makes a feature and what is the importance of the correlational structure of the environment. One of the questions I have is where do you see in this type of architecture or this type of setup for extrapolation beyond the kind of set of training features that you've already experienced? How do you generate new combinations of things?
Well, if I already had that, I wouldn't be able to go any further. I would only be able to interpret things which are either things I've already seen or things which resemble things I've already seen. I mean, it doesn't have to be exact matches. There's nothing clever here. So I mean, anything that that involves sort of rotating models in your head, there's none of that. It really is just view-based learning. But I think that's interesting for a long time, people in computer vision were trying to solve how do you recognize objects by having 3D models that you rotate and then you match them with the input and so on. And that's what has been dropped completely. I mean, these guys from Google now have just completely wiped the slate clean. I mean, nobody is going to try and do 3D models and rotating them now, because you can do it so much simpler with just view-based massive training and so on. It's maybe it's discouraging because in the sense that it doesn't look particularly clever. I mean, it's just a bunch of neurons and an STDP rule, but it does actually deliver, I think, probably.
One of the significant factor in visual perception is symmetry, and it seems like natural perception really relies on the symmetry in many ways. How would you incorporate that into your unsupervised learning? Do you have any idea about it?
Okay, so off the top of my head, we know that the left and right hemispheres have these closer connections. So an object which is symmetrical will tend to work better because it gets reinforcement from the other side. That's not going to help the symmetry for an object. It will help learn more efficiently. Objects which are symmetrical about the vertical meridian. Do you believe it? But yeah, you're right. I mean, symmetry is very important to recognize the objects, and then there's this sort of amazing stuff on how you can reconstruct the 3D shape from a like 2D view. It looks very tempting. I wouldn't know how to do it in this.
That's a lot more clear. Any other questions? One last call. No, okay. So thank you, Simon.
Well, thank you.